So now we'll talk about some different ways of using this and do a little example. So we talked about using slope. Now we're going to go in the other direction to try to understand what's going on here. And in some ways, this direction is a little more intuitive for us. Um, so if we look at the area under the curve, that's going to tell us, that is the integral of W. The area under this curve is going to tell you how much V changes from point C to point D, right? Delta V, the change in V, is the integral of that curve, right? And so from C to D, we have a negative integral, and V goes down. Now, why is that? Well, as we think about from here to here, at point C is, again, with this support, is holding up this entire load here. At point D, it's only holding up the load from here to here. So point C, in effect, is holding up a bigger part of this load, and so we would expect that shear to be bigger. So as we take this integral, we're saying, well, how much less load is D holding up than C is? Okay, so we go from C to D. As we do that, our shear is going to go down, and it's going to go down by the amount of the load within that section. Okay, then we can do the same kind of thing here and say the integral from C to D of V is that area under the curve. This is positive, right, because our shear is positive here, and that means our moment is going to increase that amount. Okay, delta M, the change in M, is equal to the integral of V. This can be more useful in some ways because we oftentimes know what W is, right? And this allows us to move, somewhat intuitively from W to V to M. Anytime this load is downward, as we pass a load, V is going to go down. If the load is concentrated, it's going to go down really quickly. We're going to get a discontinuous shear function. Okay? So if we look at this cantilevered beam, V0 is high because it's next to the support, right? And we can see that on our plot down here. But as we move from 0 to L, the load is the same, right? This support is holding up this load and that load. At this section, we're also holding up that load and that load. At this section, we're also holding up that load and that load. So the load being held up by the shear force is the same all along here, and so our distribution diagram shows that. It remains constant. If we took the integral of W from 0 to L, we'd find it was 0, and so our V does not change. Okay? At L, we get a large negative load, right? And that means right here now, instead of holding up 2P with our shear, here if I take my section, the shear is only holding up 1P, right? And now I get this big jump down in shear, and again the shear stays the same because my load doesn't change from L to 2L. Now how does that look on our moment diagram? We don't get a discontinuity, but we get a moment without a definable slope there, right? So we get a switch there. So here we have a big moment because it's holding up all of this. Our moment gets smaller and smaller, in effect, because our lever arm is getting smaller. Right here, our lever arm is from there to there, and from there to there. Once I get here, my lever arm is quite a bit shorter, right? So I am getting a smaller moment as I move along here. But then I get a significantly smaller moment when I pass P. Okay. So you can see we can use those same, same idea of sort of integrating over section to think about the changes in V and X. So we'll do a quick example here. So here's a nice cantilever beam. It's lovely. It's friendly, kind, nice cantilever beam. Okay, with a load distribution. Now first just draw a free body diagram because we're going to need to know what those support forces are. And then we'll have some Moodle questions here. So we'll kind of talk them through a little bit. So the first one is our internal shear force just to the right of the support going to be positive, 0, or negative. So what's our shear force here? Okay. Remember that if we look at the left section here, that shear arrow points down. So you might draw a little section diagram and think about whether that's a positive, 0, or negative shear force. I'm going to go on to the next question, so you can pause if you need to. Now use the integral method just to describe how Vx will change with x. Okay. Remember the integral method. We're going to integrate w from, say, here to there. That's going to give us a value here. Remember that this is a downward force. So we're going to have an integral from here to here. That's going to tell us how much v is going to change. Okay? So you can, we know that v is going to start positive if you figured this out before, right? We're going to have a high positive shear right next to our support. Now we're going to say, as we go from 0 to L, what's going to happen to that V? Think about if I took an integral from here to here, how much would I change? If I took an integral from here to here, how much would I change? Here to here, and then here to here. What's happening to that change? Now we want to think about what's that end point, right? So we have some sense of a curve here. We know we start if we answered Q1 correctly. We know that we started positive. Here, if we took an integral, we could say, oh yeah, that first integral is going to be negative, so v is going to change in a negative direction, but not much. And then v is going to change in a negative direction by a significant amount. And then by the time we get here, v is going to be changing in a negative direction fairly quickly. Okay? So now we just need to know where's our endpoint, right? So what's our internal shear right at the end? Again, kind of pause if you need to. I'm going to go on to the next slide. And our fourth question, so our moment function, so here's our function for v, right? Our integral, we know we have got a positive shear here. We're going to get a small change downward because of our integral, up to a large change because of our integral. Okay, so we end up with a curve that starts going down slowly and then goes down more quickly. Our shear here at the end, question 3, has to be 0, right? Because once we get to that end point, there's basically no load to the right if we go very close to the end point. And so it's not holding up anything anymore. And so we're not going to have any shear at the end of a cantilevered beam. So now we want to think about our moment function. Here our moment function starts with a high negative value, right? Because this is a fixed end. It's holding up all of this weight and trying to keep it from rotating this beam. So we've got a great big moment here that's pointing in this direction, which we'll define as negative here. What happens to the moment function from 0 to L? You can think about this in terms of an integral, or you can think about it in terms of slope. If we think about it in terms of slope, we're saying that the slope of the M diagram is going to be high positive, pretty high positive, medium positive, and low positive, right? So it's going to have a positive slope the whole time. If we do it by integral, we can say, well, from here to here, it's going to change a lot in a positive direction. From here to here, M is going to change a lot in a positive direction. Here to here, a modest amount in the positive direction, and from here to here, a little bit in the positive direction. So you can see we're really, both of those approaches are saying the same thing. So pause here, make sure you got an answer to Q4. And then one last one. So where is the point of highest moment at x equals 0, x equals L over 2, that is halfway, or x equals L? Where do we have the biggest moment here? And if you answered Q over 4 and have a sketch for that, you'll probably have a pretty good idea of that. Think about a fixed end. Is that going to have a high moment? Is a free end going to have a high moment? And if we look at our diagram, we can say to ourselves, okay, a free end is not going to have a moment, right? There's nothing to apply that moment to the beam. And then we can answer Q5. And that's it for this one. See you in class.